Okay, in this video we're going to go over Chapter 7, Fractions as Part-Whole Comparisons. So our authors gave us some big ideas about part-whole fractions. A part-whole comparison designates a number of equal parts, so that would be key, of a unit out of the total number of equal parts into which the unit is divided. Okay, so if I said that I divided something into 10 parts, and I circled 8 of them, that would be the fraction 8/10. The symbol AB means A parts out of B equal parts. However, one part does not mean the same as one piece. Okay, so keep that in mind. The amount in a part depends on how many equal sized parts are formed. So a third of a cake is greater than a sixth of a cake. Many different fractional names designate the same amount, and those are equivalent fractions. For example, 1/2, 5/10, 15/30. They all are equivalent. When we speak of unitizing, we mean conceptualizing the unit in terms of different size chunks. So think of how many different ways you can divvy up a case of soda. 6 packs, you have those half cans. 12 packs, so you have all kinds of ways to do it, and depending on how you define your unit, you can have a good time with that case of soda in terms of visualizing. In every fraction problem, it's important to identify the unit and to make sure that each fraction is interpreted in terms of that unit. So if your unit is three boxes, then a third of them would be 1 box. So make sure you're always going back to your unit and make sure that everyone's clear about what the unit is. In every problem, the unit must be stated explicitly, or there's enough information given implicitly that you can then work back and get the unit. Don't always use circles. Use discrete and continuous units of various types, and use units that are composed of more than one object. Okay, that variation is very, very important. Don't have your kids think it has to always be, one way. That you can help them spread their horizons in terms of their thoughts about fractions if you can mix it up a little bit for them. Okay, and lastly, do not accept a counting number as an answer to a fraction problem. So make sure you phrase your question so that you get the answer that you want to get. So, for example, back to the pizza. Do not accept back to the pizza, sorry. If I say how much pizza was eaten, I don't want an answer to be in slices. I would kind of, make sure that that was explicit to my students. Okay, unitizing and equivalence. An important fact about unitizing is that it entails the mental coordination of number of pieces and size of pizzas. An important measurement principle and an important concept for developing a strong fraction sense. Okay, remember, don't always set it up to get integer results. So here's an example. 8/12 eggs, but you can have 1 1/3 if you can have little 6-packs of eggs. Okay, so feel free to mix it up a little bit. Going on to the next page. Problems in current instruction, although fractions build on child's preschool experience with fair sharing. A lot of times, if you are asking your younger students to draw fractions and shade in different things, if you don't give them a template that already has the circles or squares or whatever rectangles you're using drawn in, you may limit your children because they have limited hand-eye coordination at that point, and they're not necessarily all little artists. So anyway, bear that in mind. Give them the tools that they need to be successful. Fraction models, there's many out there. No one model is a panacea. Don't overdo it with one model. Use different modeling techniques. And in terms of the fraction strips, if you want your children in your class to compare a whole to a half, don't cut the half strip up. Let it be in its full form, because otherwise you're going to have a mess on your hands. Okay, comparing part-whole fractions, remember the most important question is how much larger is one fraction than another, and not which fraction is larger. So it's by how much. That's where we are now. Okay, initially you're going to have them tell you which one is bigger, but then you want to be more precise and find out how much bigger, and that's really the next level of their learning. Okay, things that you can view as continuous, things like cakes, discrete units, or like marbles. And here's an example of discrete units. You can compare 3/4 with 5/8. So if I go for the same size parts, it's a process that is going to equalize the denominators. So they do a system called cloning. So a 2 clone of 4, so you want to have the denominators be the same, so you're going to multiply the numerator and the denominator by 2 of the 3/4, and you get 6/8. Doing that clone allows you now to compare these two. So I have 3/4, 1, 2, 3, and then that's the same as 6/8, okay? So now compare that to 5/8. So 1, 2, 3, 4, 5. The 6/8 has one more, so I now know that 3/4 is greater than 5/8. Okay, go on to the next one. Okay, same number of parts is a process that equalizes the numerators. Okay, so we're going to do a 4 clone. So I don't have a picture for you this time. We're just going to do it with the numbers themselves. So if you're trying to compare 3/8 and 4/9, you're going to have to do something to both of them. We're trying to compare the numerators. So multiply this by 4/4 and this by 3/3. So that's going to give me 12 32nds, and that's going to give me 12 27ths. Okay, so now what I know is that 4/9 is greater than 3/8 because the 27ths are larger pieces than are the 32nds. Okay? All right, so area models such as a rectangle area are best for introducing fraction multiplication. So if you want to multiply two fractions, let's say you want to multiply 1/2 by 2/3. Okay, what you're going to do is we have the 1/2 demonstrated here. Now we're dividing what we just drew out into thirds. And then finally, you're going to shade 2/3 of the colored region. So the result is that if you take 1/2 and you multiply it by 2/3, what are we going to get? Well, let's do the math over here. So this is 3/2 times 2/3. So it looks like I'm going to get 6/6, which is 1 whole. And can you see how you're getting that? Because look at this. This is 4 out of the 6, but then you can put these two over here, and you have 1 whole. Okay, so 1/2 times 2/3 gives you 1. Okay, partitive and quotative division. So it's another way to think about these things. In a partitive division problem, you are given the total number of groups, and you are trying to find the number of items in each group. Okay, so Mary has 50 cookies. That's her total number of groups of cookies, and she wants to divide it among 10 friends. So you're going to end up with 5 cookies each. Okay, quotative division is also called measurement division and subtractive division because you are given a measurement that can be subtracted repeatedly to obtain your answer. Okay, so how can I do that? Well, for example, if I have 12 marbles and I need to give Jim 2/3 of my marbles. So what I would do is I would draw my marbles Okay, so I drew them like that. And so here is 1/3. So I can subtract away 1/3. And then here is another 1/3. And so that's going to be 2/3 of my marbles. So that's going to be 2, 4, 6, 8 marbles. but I'm using subtraction to do that. Children should be encouraged to reinterpret a fraction division problem in terms of the meaning of division. So 2 divided by 1/2 really means how many times can I measure 1/2 out of 2? Okay, so if you have, we'll do squares or rectangles, okay, and you want to take a half out, so I'm going to divide them in half. Okay, here I can take the half out 1 time. Here's a second time, 2 times, 3 times, 4 times. So I can take it out 4 times, and I know from doing my math here that I am correct. Okay, now doing division with remainders is a bit tricky, so we're going to introduce that later, but I'll give you an idea about what I mean and what makes it tricky. So let's say we had 3 rectangles, and you want to take 2/3 out of each one. So let's divide them into thirds. Okay, so 2/3, 2/3, 2/3, and then I can take another 2/3. Now, what do I have left? Well, I have 1, which is a half of the 2/3. So I was able to do this 1, 2, 3, 4, and a half times. Okay, so you're getting a change in your denominator. That's what makes that very tricky. Okay, so that's it. So we don't really need this. So now focus on the activities at the end of this chapter, and then look at the problems in the problem set.